Hi everyone, so in this video I'm going to start with 9.1 kinematic of simple harmonic motion. So let's start. 9.1 I'll be explaining what is simple harmonic motion and all the characteristics involved in SHM. We have learned previously linear motion, circular motion and rotational motions kinematic. So when it comes to kinematic, we are talking about the displacement, linear displacement, angular displacement, and then we also talk about velocity, linear velocity, angular velocity, and then we also talk about acceleration, the linear acceleration, angular acceleration, and also all the energies involved. So what is periodic motion? It's a back and forth motion of an object about a fixed point called the equilibrium position. So we have here examples of periodic motion, but we have here three animations showing that this is a vertical spring, a pendulum, and a back and forth ball. So these are all examples of periodic motion. So in this topic, we're going to study the special kind of periodic motion, and that is simple harmonic motion. So the definition for simple harmonic motion is SHM is defined as a periodic motion without loss of energy. We don't want any loss of energy, in which the acceleration of the body is directly proportional to the displacement from the equilibrium position and is directly directed towards the equilibrium position but in the opposite direction of the displacement. So you can see that the acceleration is equals to negative omega squared x. Now notice that A is acceleration, omega is the angular frequency or angular velocity, and then the x is the displacement. So here you can see that the negative sign here and here, the negative sign shows that acceleration always opposing the direction of the displacement. So here, look at this small thing. Now, this one is the example of a SHM system. So we have three arrows here. We have displacement, which is the black arrow. We also have the green arrow, which is the velocity, and the red arrow is for the acceleration. Okay, now I zoom in for you to see it properly. Now this is the equilibrium point because it is at the center. And this one is the amplitude, which is the maximum displacement. So we have two amplitudes, the negative one, the negative A, and also the positive A. And this one, the O, is the equilibrium point. Notice that as the block moves to the left and right, the displacement increases. So let's take that positive as the right and the negative as the left. You can see that the maximum displacement is amplitude, and look at the green arrow. What happened there? As the displacement increases, the velocity, which is the green arrow, decreases. Look at how it becomes shorter as the black arrow becomes longer. So we can say that at amplitude, the velocity is 0, while the acceleration is negative because the displacement is positive. We know that in previous slide that I mentioned that displacement is always on the opposite direction of the acceleration. So you see here, for the positive amplitude, the acceleration becomes negative. And since we've learned in school that force equals to ma, where the direction of force is directly is in the same direction as the acceleration. So since the acceleration is negative, thus Fs is also negative. But wait, what is Fs? So Fs is actually the restoring force. Restoring force always pointing to the equilibrium. Okay, so this is at the positive amplitude. But do we have any information for the negative amplitude? Yes, we do. Look here. So as the displacement is negative at negative amplitude, hence the acceleration becomes positive. So So restoring force also becomes positive. And notice that the velocity is 0 at maximum displacement. Now, what happened to the equilibrium? At equilibrium, so we have two situations. The first one, if the object moves to the left, then x is 0, obviously, because at equilibrium point, the displacement is 0. And since the displacement is 0, acceleration also becomes 0, hence the restoring force also becomes 0. But look at the velocity. Now the velocity becomes negative because the object now moves to the left. But what happens if the object at equilibrium but try to move to the right? So again, the displacement is 0, acceleration is also 0, as the restoring force is also 0. But look at the value of the velocity. Now it becomes positive maximum, right? So this one is the summary of what that I've explained just now. Alright, this one is the examples of SHM system. We have simple pendulum, we have frictionless horizontal spring oscillations, and vertical spring oscillations. These three use the same concept that I've just explained just now, where the velocity is 0 at amplitude and maximum at the equilibrium, and the acceleration is maximum at amplitude, but opposite direction to the displacement. Alright, let's take a look at the terms used in SHM. We have equilibrium position, I've introduced you. We also have displacement, and if the displacement is maximum, it is called amplitude. And then we also have period, which is the time taken for one complete cycle, and the unit is in second. Frequency is the number of complete cycles in 1 second. The unit is hertz, and the equation is F equals to 1 over T. Next, we have angular frequency or angular velocity. We have two equations here, omega equals to pi over t, or equals to 2 pi f, depending on what information we have. So the unit is in radian per second. And next is restoring force. So restoring force is a force that tends to bring a system back towards equilibrium. That's why we can see that the acceleration just now, which is the red arrow, yeah, the red arrow, always trying to move to the center. Okay, so we know that restoring force, like for this one, is a spring, so Fs equals to negative Kx. So this is you can see that the red arrow over here is the restoring force, and the blue arrow is the displacement. It is always, restoring force is always pointing to the equilibrium point. So I want to show you this one. So you can see here we have three positions. At displacement equals to 0, Fs is also equals to 0. And if the displacement is positive, Fs, restoring force, becomes negative. And if the displacement becomes negative, Fs now becomes positive. They always oppose each other. So SHM is a back and forth motion that actually a circular motion. So with time, we can produce a displacement graph, and we can get a sinusoidal graph like this. So moving in anti-clockwise circular motion like this, one complete cycle is 2 pi here, which is equivalent to 360 degrees. And the time taken for one complete cycle, this red axis, is 1 period. So one complete cycle gives us 1 period. And then this is the wavelength. One complete cycle is 1 wavelength. And then this is where the equilibrium position is. This is the positive amplitude, and this is the negative amplitude. Now let's say that this red ball moves here. So it is displaced this much. Let me change the color of the pen. So it displays this much, and the angular displacement made is theta. Alright, so if I want to take out this triangle, which is the theta, oh, sorry, so let me see, I'm going to take this triangle, so this is actually x, So I want to take out these triangles for you to see clearer. So this is R. So this is R is actually amplitude, because amplitude is the radius. Since the radius is always constant throughout the circle, so this is amplitude, and this is the X, and this is the theta, right? Look at here, this is opposite and hypotenuse. So opposite and hypotenuse gives a sine. So sine theta equals to X over A. You can see that X over A equals to sine theta. And when we rearrange it, we're going to end up with X equals to A sine theta. And we learned in previous chapter that theta equals to omega t. Hence we put it in, then we can get SHM displacement equation, which is X equals to A sine omega t, which look, it matches the shape of the sinusoidal graph. So this is actually the sine graph, right? Notice that although we can put X equals to A sine omega t, we can also put the expression as X equals to A cos omega t minus half pi. So I put it in a simpler form, put it in a table form. So you can see here again that this is a displacement time graph. So the equation is X equals to A sine omega t. These are all the symbols, or the meaning of all the symbols. Remember that omega is in radian. You have to put your calculator mode in radian when you try to do the calculation. So we have this A, X equals to A sine omega t, or you can also put it as X equals to A cos omega t minus half pi. Next, we go to the graph of velocity time. So we've seen that previously, that if you remember, the black arrow has maximum displacement, but the green arrow becomes shorter and eventually becomes zero as it reaches the amplitude. They contradict each other. So if the displacement time graph is sine graph, hence the velocity becomes cos graph. So that's why we got this kind of shape of graph. It actually comes from the differentiation of displacement with time. So we differentiate v equals to dx over dt. When we differentiate, we're going to end up with v equals to a omega cos omega t. So for maximum velocity, you can straight away use v max equals to a omega if the question is asking you for that. At amplitude, like I said, the velocity is 0. At equilibrium position, velocity is maximum. And in terms of displacement, we also have the equation for that. So v equals to plus minus omega z a squared minus x squared. So remember that you have to put in this positive negative sign, because we have to the left or to the right displacement, hence we have to the left and to the right velocity. Next, we have acceleration time graph. Notice that for the displacement graph, it is sine graph, but it is a positive sine graph. But for acceleration, it is also a sine graph, but this time it is a negative sine graph, because they are always opposing the direction of each other, but they are directly proportional. So when you do the differentiation, you're going to end up with a equals to negative a omega squared sine omega t. Look here that we have the negative sign. And for the maximum acceleration, which is at the amplitude, a max equals to a omega squared. And then in terms of displacement, we're going to end up with a equals to negative omega squared x. So the last one is the energies, graph of energy. So we have two kinds of energy, kinetic energy, and we also have the potential energy. So we take a look at the first one, which is the potential energy. So potential energy, as like a pendulum, it moves back and forth. The potential is the biggest, is the highest at amplitude, and that's why you can see that at amplitude, here at the blue line, has the highest potential energy, and as it goes back to the equilibrium point, this is where the height is 0. So that's why the potential energy is 0, and as it goes back up to the amplitude, it becomes maximum again. So the equation for the potential energy is U equals to half m omega squared x squared. Next, we go to the kinetic energy. So the kinetic energy, if you see that a pendulum moves back and forth, it's actually, okay, here back and forth, it is maximum at the equilibrium point because it is where the object is the fastest. So we can see that at amplitude is 0 because of the velocity is 0. And then when it moves back to the center, which is at equilibrium, this is where the kinetic energy is maximum. So the equation for that one is K equals to half m omega squared times a squared minus x squared. Okay, so in total, we know that in the definition of SHM, we say that there is no loss of energy. Do you remember that? So look at here. We have combined the two lines, the potential energy and the kinetic energy together. But the total energy is the black line over here. They are all consistent throughout the process of motion. So the total energy, the E, which is the black color, K is the yellow color, U is the blue color. So E equals to K plus U. E is the total energy, K is the kinetic energy, and U is the potential energy. And we can see that the equation E equals to half m omega squared A squared. Alright, so total mechanical energy for a simple harmonic oscillator is directly proportional to the square of amplitude. There is an interchange of energy between the potential and the kinetic energy, but the total energy remains the same. So these are all the equations for kinematic or SHM. I'm going to go to the next video after this with 9.2. Thank you.